Hi everyone and welcome to this lecture, and today we are going to model a simple harmonic oscillator and the damped harmonic oscillator. As you can already tell by the title, that is, we are going to simulate the classical spring mass problem in two different ways. So let's get started. For starters, we want to initialize our parameters, that is the mass of the spring. Let's call it m. We take it to be 2. Then we can have a damping parameter b that will be equal to, let's take it 2 as well, or you can have 2.5, let's say. And our spring constant k, let's say it's 25. After that, what we're going to do, we're going to specify some initial condition that is given by the x0. X0 means the initial position of the oscillator. Let's say it's 3/2. And also the initial velocity denoted by v0, and this will be 0. Next thing we're going to do is that we're going to type solve, and this is where we solve the differential equation, or you can just have it like this equation. You type in the equation, that is mx of t, and there's a double prime, that means the second derivative, plus b x prime of t plus c, sorry, not c but rather k, x of t, and this is equals 0. So we have our equation, we have our initial condition. So now what we want to do, we want to generate a solution using dsolve. And after using dsolve, you just type a list that will take the equation and the initial conditions like this: x0 equals x0, that is the initial position, and the initial velocity as v0. We want to have x of t. Our independent variable is t. So far so good. Let's run it. You can see that we already have our solution over here. So let's suppress this solution and declare a new function, capital X of t, where we will just replace this whole thing. Notice that we can make this damped harmonic oscillator into a free oscillator if you just take b equals to 0. So let's try to do it. Yes, this worked successfully. Now let's see whether it actually worked or not. So far it seems good. So just draw some plot. You can see that it's plotted successfully, but we are not getting all the ranges in the y-axis. So to get that, we have to type plot range all. So you can see that it starts from y equals to 1.5 and then it dies down pretty fast. So if you just take b equals to 0 now and run this cell, you can see that this is a sinusoidal solution. That is true for a non-damped oscillator, that is the free oscillator, because this term over here, this will be gone, right? Okay. And now, in fact, if you just take k equals to 0, it won't be a spring mass problem now. Let's take b equals to t and see. Yeah, so this is something else right now. So this is how you can vary the parameters to get your desired solution. Let's stick with b equals to 2 and k equals to 30 now instead of 25. So yeah, this is our solution. Okay, it worked really well. Again, suppress it. But now what we want to do is that we want to see also the dynamics that varies over time, that is the kinetic energy, the potential energy, and the total energy, and we want to see how they change. So let's define our kinetic energy as k of t. Okay, let me choose small k. Oh no, I cannot do that because small k is already there. So let's just type small ke. Ke means kinetic energy, and this will be a function of time. So this is 1/2 m. Then you have your, notice that in this line capital X is containing the function that is coming from dsolve that was initially stored in solution, and now you just have to put capital X t, there's a prime, put a square, that is our 1/2 of mv squared, right? Okay, so kinetic energy is done. How about potential energy? So potential energy, let's call it PE. It's also a function of time because potential energy will depend on the position, and this position itself is a function of time. So again, this will be just 1/2. Okay, let me put an equal sign over here. There will be a k, and there will be a capital X of t, and there's a square, that is a kx squared. And the total energy, let's call it just small e, will be the summation. It's also a function of time, so kinetic energy plus potential energy. Okay, now let's try to plot all of them together to see whether we are getting anything or not. So kinetic energy, potential energy, and the total energy in a single graph. And again, we want to use the same range. You can also vary the range if you want. Let's say I want to have for 0 to 15 or 12, because we saw earlier that the plot was dying down, that is the oscillation was dying down really quick. So again, I want to have my plot range all, and I can just get away with typing plot theme detailed. It will take care of the labeling automatically. You can see that I'm getting the potential energy but not the other things, that is the total energy or the kinetic energy. So something is going wrong, as you would expect from here. That is, this derivative over here, this is not coming by, because see, when you make replacements like this, it will only take this one, that is just x into capital X, but it won't be able to evaluate the derivative. So there are many ways to get rid of this problem, but for us, what we're going to do is that we'll type dsolve value. That's the easiest thing you can do in case you see this kind of problem. So let me just suppress this thing and get rid of this cell. And what will happen when we do this value thing is that it will give us something like this, and you can see there are some really big and lengthy line of warning, but don't worry about it. So take this function and just get rid of this whole thing and just use this over here, and now everything should work just fine. The reason that was not working because small x of t was getting replaced into capital X of t, but it went as a list. So only the plot thing that will involve only capital X of t should work, nothing else would work. And if you want to use this replacement thing after you replace the solution, be sure to change the variables as well. That for example, instead of small t, you could have taken capital T, and you need to make corresponding changes over here as well. So in our case, just we are going to approach this more simply, not in a very complicated manner. So let's try to do all this together, and hopefully everything will be all right. You can see that there is a part specification longer than the depth, and there are still some warning signs. So let's see what is happening. Yeah, now it's okay, but it's just showing this output over here. So yeah, this will be here, so let's not care about it much. If you now try to plot it, you can see that the kinetic energy, the potential energy, and the total energy are being plotted over here, and this oscillation starts to die down really fast after 4. So let's try to focus on those parts. Let's say 4.5. yeah, now it's better. So after this, what we want to do is that we are already seeing this thing, right? And after this, we want to put a physical oscillator in our Mathematica simulation. That is, we want to have a ball that will move back and forth with the solution that we got. And to do that, we are going to use some graphics feature of Mathematica. So let's try to put a ball first. So let me just write it down. Putting the oscillator. So the idea will be to put a point with some certain diameter, and we want to make the point move along some line. So let's try to do it. First we need to use manipulate, or you can also go with animate. So I'm gonna go with manipulate. Inside this manipulate, we are going to put our graphics options. So let's type graphics, and here, since we want two things, the one of them is a point that will serve as the oscillator itself, another one is a line that will represent the stretchness of the spring, that is whether the spring is stretched or compressed and so on. So first you make a list, and inside that list you are putting two objects. One of them is a point and one of them is a line. So let's first put a point. So just type point size, and let's take the point size to be 0. Okay, so 0.25 is a lot, so just type 0.04. And now I want to make the point move as time goes. So the point's coordinates, that is since this is a one-dimensional oscillator and we are only getting a time-dependent function as capital X of t. So okay, so now I see why this was appearing over here, because I didn't suppress it. Okay, so the only time dependent thing was this capital X of t, right? And this corresponded to this solution, and this is the coordinate for the oscillator itself. So now you want to put the point. Oops, sorry. And this point will have a x coordinate and a y coordinate. So the x coordinate will be capital X of t and the y coordinate will be 0, right? Alright, so we have put the points, and then what we want to do here is that we want to make a line that will stretch and give us a representation of the spring itself. So inside, so this line command I just typed right now works in some way. Let's say it will take a list first, and inside that list you can have as many lists as you want. So here you can see that this is one list inside a list, that is, it's another list, and it will contain two entries. The first one will correspond to x and the second one will correspond to y. Similarly here, the first one will correspond to x and the second one will correspond to y. So what does this line command do? It just, if you specify 2 points, then it will just draw a straight line between those 2 points. That is, if you had it given as 1 1 in here, let's say over here, and if you had typed 2 3, then it would take 2 points in the 2-dimensional plane, that is 1 1, that is the x coordinate 1 and y coordinate 1, and from that point it would have drawn a straight line to the point that has coordinates of 2 and 3. But since we want this line to represent a spring, it should stretch and it should expand, right? So what we're going to do is that, let's say my spring's endpoint, one endpoint is attached to the oscillator, another one is attached with a pin that is put it on the ground. So let's take that point to be 0. Since it's a one-dimensional problem, all the y coordinates will be 0, and here I'm doing x of t because I want that line to vary in length, so that's why I'm giving this x of t over here, and since the y coordinate is 0, we'll just put 0 over here. So we have successfully putted the line and its coordinates and the point. The next thing we have to do is that we have to specify the plot range, and this is important because if we don't specify the plot range, there might be a chance that our oscillator will go out of the graph or the animation. So that's why inside this graphics we want to have a plot range. So let's have a plot range of something like this. We want to specify our x's and we want to specify our y, so x from -2, or okay, let's just go with -2, and we can change if we need it. So from y, it's also from, let's say, -1 or minus, yeah, since our diameter will be just 0.08, so we can just call it from -1 to 1. Okay, we are done, I think. And finally, you want to have the t that you are going to manipulate. So inside this t, I want to manipulate t from 0 to, let's say, 10, and I want to see what happens. Let's try to run it. Yeah, we have successfully put the oscillator over here, and as you move the slider, you can see that this is indeed the oscillator itself. And instead of manipulate, you can also go with animate. And if you run it, you can see that it gives us a very nice animation. So this is the part that we have put the oscillator in Mathematica, but now what we want to do is that we want to see this whole scenario, that is the potential energy, kinetic energy, total energy. You can even get the position that itself is a function of time. So in case here you want to type x of t and just put a comma over here and run it again, you can see that now there are 4 graphs and x of t is the lowest graph over here. Alright, so this is how you can get all the information that you want. And now what we want to do, we want to put this oscillator and this graph together, and we want to see what happens when the oscillator is where. And we will do that using another line, but you can see that taking the y range to be between 1 and -1 creates a very big box like this. So instead of that, let's just take 0.5 and 0.5. This is more of a suitable thing, but let's just reduce it more. Let's take 0.1. Yeah, this is nice. This is good. So now we want to put all of this information together. So final touch. In this final touch, what we are going to do, we are going to take this plot over here, that is this one. We are going to take this animation and we are going to combine them together. So how can we do that? Let's try to see it. Okay, there is an extra cell, so let me just get rid of it. To do it, what we need to do now is to put this plot thing inside our manipulation bar or the animation bar. And we talked about another line as well, so we will see how we can do that, how we can achieve another line that will move along with the oscillator and give us a physical indication about what's going on. So let me just type all these things again. you type animate. Inside animate, you can put the plot over here, that is this one first and the ball secondly. So let me just copy it. I don't want to go through the trouble of typing it again. So yeah, this was our oscillator thing, right? But now we have something more, because we want to have a plot of our graph as well along with this animation. And to get everything done as we expect, we have to actually use something new. So it's easier to do with manipulate, and later on we can see whether animate would work or not. So use manipulate, and inside this manipulate you have to declare a list, because now you are declaring not only a oscillator but also another graph as well. So okay, so which one is the second bracket over here? See, these are very confusing things, because this graphics is ending over here, so you have to put this second bracket over here and you put a comma and you take this plot over here and you copy and paste it so that you don't have to type all of these things again. But there is a catch right now, because the catch is, you see that in this plot all of them are functions of time, and you are also plotting over time, also you are manipulating over time. So what you can do is that now you can just, it's one of the oldest trick in the book from Mathematica, that once a function is declared you can just change the argument and the it will just take the definitions that was declared before. For example, in case of t, if you type x of 2, it will give you t equals to 2 thing, or if you type x of m, it will, instead of t, it will provide you m, because Mathematica can do symbolic manipulations. So instead of t over here, let me just call it x, small x. Okay, not small x, let's go for capital T. So just replace them with capital T so that our plotting and the manipulation or the animation is working properly, because if you don't do it then it won't work properly. So yeah, and after this is done, there are two more things we need to do. That is, one of the thing is that we want a black line like this, and we want it to move over this curve as this oscillator moves like this. So let me show you what do I mean by that. So to do that, inside this plot we want to, that is over here, inside this plot we want to have something called an epilogue, and this epilogue will help us to put a line. So after this plot thing, okay, so we can see that the plot is ending over here. So it's another one of the customizations that you can see that this is the epilogue, and if you use epilogue function you can even provide curves as well. And here we want to again put a line, and this time our line will move with the oscillator itself, right, as time goes on. That is, it will move across the time, and we'll see what is happening with the oscillator. So to move it with time, we want to do the following, that is, it's a dynamical thing. So the only thing that is dynamical over here inside this command is the small t. So these are the things you have to be a bit careful, because if you use capital T, it will just be a static thing. So, and even if you just type capital T, it won't be able to plot anything. So type dynamical T, that is capital T, and okay, sorry, not capital T, small t, and we want this to go from y from 0, that is over here, to the all the way up. So all the way up for this is 35 from this. So it starts from 0 and it will end at 35. And you can see that the distance between the two x coordinates is 0 over here. So that's why there will be no horizontal component, only the vertical component is there. So it will have a magnitude of 35. So we are almost done, and a final touch would be to inside this manipulate, because manipulate has now two things, and inside this manipulate we want to have something called a column, and we will see why this is important. So inside manipulate, type column and type @. And now let's try to run it first, because when you have this column thing, it's like the things that are in the list are now two columns, and you are getting two separate informations and you are plotting them together. So let's try to do it. We see something over here, and let's try to move the slider. Yes, you can see that the slider is moving as time goes by, and you can see the oscillator as well that is oscillating over here. So this is a rather small image, so instead of manipulate, let's now use animate so that we can automate the animation. Animate, and what we want to do is that we want to put our image size into medium. So to make the image size medium, you just have to make the plot bigger, and that can be done with just outside of these things. So let me just type image size. Hopefully this is working. I don't know why there is a red. Okay, sorry, it was not under the plot, rather it was under manipulate or the animate. So here you just have to now it's far better. So this is how you can easily simulate a oscillator itself, and if you want the animation to be smoother, you can just make the time step, that is the interval between two adjacent points, like this. For example, I want this to have a 0.0004. You can see it's going a bit slower than before, and we have all the information that we need. So this is how you can start from very scratch and get a very nice result. And if you just take B to be 0, then you can just put the simple harmonic oscillator over here instead of the damped oscillator. Also, instead of taking 0 on the right hand side over here, you can just put a sinusoidal driven function that will generate the solutions of a driven damped oscillator. And this will be it for today. I hope you enjoyed it, and thank you.